Hello everyone, welcome back to my YouTube channel. My name is Vedrukas and in this video we will talk about logistic regression and gradient descent in logistic regression. If you are watching this video first time, please do not forget to subscribe my channel and like the video. It will give some confidence to me to create more videos. Before starting, if you are looking for more in-depth explanations and resources, make sure to check out the link to my blog in the description below, that is geekycodes.in. So logistic regression. Logistic regression is a commonly used algorithm for binary classification, which means it is used to predict the probability that an input belongs to one of two classes, that is labeled as 0 or 1. Despite its name, logistic regression is a classification algorithm, not a regression algorithm. Logistic regression model uses the logistic function, also known as sigmoid function, to map the linear combination of input features to a value between 0 and 1, which can be interpreted as the probability of belonging to one of the classes. The logistic function is defined as sigma of g is equal to 1 upon 1 plus e to the power minus j, where z is the linear combination of input features and weights plus the bias term, that we can say z is equal to theta 1 plus theta 1 x1 plus theta 2 x2 plus dot dot plus theta n xn. Here theta represents the weights of the features and x represents the input features. The predicted probability y hat that an input belongs to class 1 is given by applying the sigmoid function to z. Y hat is equal to sigma of z equal to 1 upon 1 plus e to the power minus. To train the logistic regression model, we use a cost function called the log loss, also known as cross entropy loss. For a single data point x comma y, where y is the true label, 0 or 1, the log loss is defined as L y comma y hat is equal to minus y log y hat minus 1 minus y into log 1 minus y hat. The goal of training is to minimize this log loss across all the training data. Now, gradient descent in logistic regression. To derive gradient descent algorithm for logistic regression, we will start with log likelihood function that we calculated earlier. Given a dataset with m data points and their corresponding feature vectors xi and binary labels yi, or that is 0 or 1, the log likelihood function for logistic regression is L theta is equal to sum of I is equal to 1 to m yi log y hat I plus 1 minus yi into log 1 minus y hat I, where theta is the vector of parameters, that is weights to be learned, and y hat I is the prediction probability for the ith example. The predicted probability y hat I is given by the sigmoid function, that is y hat I is equal to 1 upon 1 plus e to the power minus theta transpose xi. So the predicted probability y hat I is given by the sigmoid function y hat I is equal to 1 upon 1 plus e to the power minus theta transpose of x of I. To perform gradient descent, we need to find the gradient of the log likelihood function with respect to each parameter theta j. Differentiation of L theta by with respect to theta j is equal to sigma m is equal I is equal to 1 to m of yi minus y hat I upon y hat I into 1 minus y hat I into xij. Now the gradient descent update rule for each parameter theta j becomes theta j is equal to theta j plus alpha into differentiation of L theta with respect to theta j, where alpha is learning rate. Putting everything together, theta j is equal to theta j plus alpha into sigma I is equal to 1 to m into yi minus y hat I upon y hat I into 1 minus y hat I into x of ij. Repeat this update equation for each parameter theta j until the convergence or a predetermined number of iterations. In practice, this update equation adjusts the parameter in the direction that reduces the log loss, leading to the better predictions over time. The learning rate alpha determines the step size of each update, and it is important to choose an appropriate learning rate to ensure stable convergence during training. So if you like the content of this video, then please do not forget to subscribe my channel